Hello. Now we will calculate the capacitance of a capacitor where the dielectric is partially filling the capacitor. In this case, the dielectric is having the same width as the width of the capacitor, but the cross-section area of the dielectric is lesser than the cross-section area of the capacitor. The cross-section area of the capacitor is A, and for the dielectric it is A1. Okay. So in this case, to calculate the effective capacitance, because we already only have a formula to calculate the capacitance when the dielectric is completely filling up the capacitor. So in this case, it is partially filling it up. So what we will do here, we will cut this capacitor. We can cut the capacitor till we are cutting it perpendicular to the cross-section area. Okay, so we cut the capacitor. So by cutting the capacitor, we got two capacitors. And after cutting the capacitors, we will join them in parallel. So it is same. So we'll have two capacitors here, and they will be joined in parallel. So the first capacitor, which is having a cross-section area of the A1, it is completely filled by the dielectric of dielectric constant K. And the second capacitor, which is filled by the air, is having a cross-section area A minus of A1. Width, both of the capacitors are having the same width D. They are connected in parallel. I am calling this one as C1 and this as C2. So first I'll calculate C1 and C2, then by using the parallel addition formula, I'll be calculating the effective capacitance of this system. Okay, so we know the formula for capacitance is A epsilon upon D, where epsilon is permittivity of the medium inside the capacitor. So for C1, it is filled by the dielectric of dielectric constant K. So the C1 will become A epsilon naught times of K divided by D. And the C2, which is filled by the air, it will become this is A1, this cross-section area. A minus A1 epsilon naught divided by D. And both of them are connected in parallel. Since both of them are connected in parallel, so the formula for effective capacitance will be C1 plus C2. This is the formula for when the capacitors are connected in parallel. So we'll write the values. 1 upon D we will take common. So we'll have A1 epsilon naught K plus A minus A1 epsilon naught. So the C effective will be, you see the formula here, A epsilon naught plus K minus 1 A epsilon naught divided by D. Okay, go see this one and the A1. I've taken common A1, sorry, this is A1. So this becomes the effective capacitance for the system. Now if I combine this topic with the previous topic, what we learn? If I'm having a capacitor, I can cut the capacitor parallel to the cross-section area, as well as I can cut the capacitor perpendicular to the cross-section area as well. So if I'll be cutting the capacitor parallel to the cross-section area, the portion which I have cut, those portions should be connected in series. Then we have to use the series formula. But if I'm cutting it perpendicular to cross-section area, the portion we are getting here, they should be connected in parallel. Okay, we can cut. Either you cut parallel or you cut perpendicular. There is no problem, but after cutting the system, cutting the capacitor, how you join, it will depend upon how you are cutting the capacitor. Okay, so that's how we calculate the capacitance of the capacitors when they are filled by dielectric, but not completely, partially. We cut the capacitors and we convert the capacitors into the structures for which we have the formula, like this kind of structures. Okay, I hope you understood that. Thank you.